my math YouTube channel. So I'm back with another example on trig techniques, and this time this is like completely different than any of the other examples that we saw. I think we did 4 of them so far where we used the trig techniques, but in those examples we were able to see a trig function, and then from there we used the identities and use the right substitution, which I like to call also as clever substitution, and then we were able to evaluate them. Guys, in this case we don't even see a trig function, right? There's no trig function here, but one has to remind themselves the different trig identities, and those trig identities actually give us a clue what we have to do and how we have to actually start this particular problem. But guys, before we do any of that, if we look at this particular problem, then we ask ourselves, are there any direct ways, or are there any other ways of actually evaluating this integral? And if you try to think about this and try to use different techniques and methods that you have learned so far, those would not help us to actually evaluate this integral. So one has to think if you want to think about think in the way that think outside the box to kind of evaluate this. And thinking outside the box here is more like thinking in terms of introducing some sort of trig functions. But we cannot just bring in any trig function. We know there's 6 of them, 3 are the basic ones and the other 3 are the reciprocals. But one has to be able to, I think that is one of the reasons why I like to call this as a clever substitution. This is that problem where one really needs to use that clever substitution. Okay, so what I'm going to do here is I'm going to write 3 trig identities, and from those three trig identities we're going to choose one and use that and substitute and then take it from there. So guys, we may not be able to use all 3, we may be able to use any 1 or any 2, and we will decide, or we will choose the one of them and then we'll start from there. So guys, the 3 basic trig identities which you may have already seen in your trig class or you already remember, I'm going to remind you. The first one being sine square theta plus cosine square theta is 1. These are all called the Pythagorean identities. That is one of them. The second one is 1 plus tangent square theta equals to secant square theta. And the third one is 1 plus cotangent square theta is the equivalent to cosecant square theta. Guys, these are, there's so many more trig identities, but these are the 3 basic Pythagorean identities. And in this case, we may have to just use just one of them. So guys, here I am going to go back and look at the denominator. I have a 4 plus x squared. So there's a plus here. Since there's a plus here, that kind of suggests that I may want to use something like this, because this 4, I can transform this 4 to a 1 by just dividing by 4, right? So if I can make this 1, then this is going to resemble more like either this one or this one rather than this, because you can see on the left hand side here, of course there's plus, plus and plus in all 3 of them, but there's no 1 here, right? There's 1 on the other side, but we don't want 1 on the other side here. We can transform this 4 by dividing it by 4 and make it look like 1, but here, guys, there's no 1 here, but both of them have 1s. So it is up to you whether you want to use this one or this one. I'm going to choose the second one, and then I'm going to take it from there. Guys, you may want to try using the second one, third one, that's fine, but let us use the second one and see how we can use that to actually simplify or make sense out of this integral. So in order to do that, guys, what we're going to do is we're going to use the right substitution, and in this case I'm going to say let my x equal to tangent of theta. So I'm using this second one. And guys, again, this is something, if you are seeing it for the first time, you would still be surprised, and you would be wondering how is that going to simplify and help us to evaluate and solve this. Guys, you have to just look at the steps, follow the steps, and you will see how things work out once you choose the correct substitution. But I wrote these 3 so that at least you can see 3 of them in front of you, and then from here you can at least see for now how we can relate this to one of these. Okay, so if there was a minus here, guys, then we may not be able to use any of these. Then we may have to rearrange or do something else or use something else. Here, since there's a plus, so I was able to use this number 2. From here, guys, the second step. So once you start the substitution method and you substitute something, and then the second step we take the derivative, right? So in this case we take the derivative, but we take the derivative of this dx with respect to theta, because here I have a function theta. So dx over d theta And we know the derivative of the tangent is secant square theta. You should either have the derivative table or derivative formulas in front of you, or you have to remember them. Guys, from here, usually most of the times we have to solve this for dx, and in this case, let us also solve for dx. So dx will be secant square theta d theta. I'm going to box this guy and this guy. And once we do step 1 and step 2, then we know in step 3 we bring those two together, put it back in the original function and try to simplify. Okay, so let us go back and put it back in the step 3, step 2, step 1. Let us put it back. Guys, integral 1 over, and here I have square root of 4. So I'm going to write that 4. And then I'm sorry, I wanted to actually start with a 2 here instead of just tangent theta, and you will see why I want to choose 2 and not just tangent theta. So obviously there is going to be a 2 here as well, there's going to be a 2 here, sorry about that guys, and you will see why I actually chose that 2, because we want a 1 here. So you will see once we simplify this step, you will see why we chose 2 tan theta and not just tan theta. Because if I just choose tan theta, then that will not help me to get, I can still get a 1 here, but it will be a little more complicated. So it's convenient to start with 2 tan theta rather than to start with just tan theta. So this is going to be plus, and then I have to do what? X square. So x square is 2 tan theta whole square. So 2 square is 4, and then I have a tangent square theta. Okay, and then what do I have? I have dx. What is dx? Dx is 2 secant square theta d theta. So guys, this worked out very well, because this was in terms of x, but by using this substitution in terms of theta, we were able to finally get rid of the x's, and everything is consistent, like everything is in terms of theta. Now let us simplify and see if this substitution actually helped us to simplify this. So from here, let us take it up here. So guys, this is going to look like integral 1 over square root of. So guys, this is, now you will see why I wanted to choose 2 tan theta and not just tan theta. Guys, this 4 and 4, I can take out 4 as a common factor, or a greatest common factor, and what is left inside the parentheses? I have 1 plus tangent square theta, and that is exactly what I have here as an identity. Guys, just by looking at this, we may not be able to see how we can get 1 plus tangent squared, but by using appropriate substitution, now we are able to get that 1 plus tangent square theta. And guys, that is real mathematics, when one has to like use some extra things in order to and then manipulate and then do the process and steps to see what one actually wants to see in this case. Okay, so 1 plus tan square theta is right there, and then times let me put that times 2 secant square theta, and then there's a d theta. Okay guys, let us simplify this. We can simplify further. This is, let us just bring it together. It's 2 secant square theta, because 1 times that is just 2 secant square theta. Guys, downstairs, square root of 4 is just simply 2. And then I'm left with square root of 1 plus tan square theta. But what is 1 plus tan square theta? 1 plus tan square theta is equal to secant square theta. So we got to write secant square theta here, d theta. Guys, you can already see that things are getting simplified, and that's why we wanted to use this right substitution, so that we can simplify things and we can evaluate the integral. We're getting closer and closer to evaluating the integral. Now you can already see that this 2 and this 2 will cross out. Okay, we are left with just integral of secant square theta. And when I take the square root of secant square theta in the denominator, I'll be only left with what? Just secant theta, and of course there's a d theta. We can still simplify. Secant square theta over secant theta, one of the secants is going to cross out upstairs. So we're going to be left with integral only secant theta d theta. Guys, all this work, first recalling the identities and then using the appropriate substitution, and then doing the methods of the steps of substitution, step 1, step 2, step 3, bringing them together, and then here again going back and realizing that this equals to secant square theta, and now simplifying this simplifies to just a simple integral of a secant theta. And again, that is something that we already know, and you can look at the formula sheet because it's a basic identity. We know that the integral of a secant theta is, and let us make some room to kind of squeeze in this stuff. So guys, what I'm going to do is I'm going to get rid of these identities here and try to do this. So integral of this, again, please look at your formula sheets. The integral of secant theta is simply natural log of secant theta plus tangent theta and then plus, of course, a plus constant of integration. Guys, this is the integral of the secant theta. You can find that on a formula sheet or in your textbooks. But guys, we are still not done because our original function is in terms of x. And the answer that we have right here is in terms of theta. And we already know that if the original function is in terms of x and we are integrating with respect to x or dx, then the final answer should also be in terms of x as well. But we know how to get it finally in terms of x. All we have to do is we have to go back to step number 1, which is the substitution step, right? And from step number 1, we should be able to get everything back in terms of x. Okay, so let us look at this first substitution step. So guys, I think I need more room. So what I'm going to do is I'm going to get rid of this, and we're going to work on getting it back in terms of x. So the first thing that I need is I want tangent theta, right? I want tangent theta in terms of x. Not too difficult. All we have to do is we have to divide both sides by 2 and we'll get tangent theta in terms of x. So tangent theta will be simply x over 2 just by dividing both sides by 2. That's good. So now I already have the tangent theta in terms of x. All I need now is I need to get the secant theta in terms of x as well. Again, guys, that should also not be so difficult because we have an identity that relates our tangent theta with the secant theta. I had already written that out here, but because I didn't have enough space, so I had to get rid of it. But let us recall that. Let us rewrite that, guys. 1, or I can just say that secant square theta is 1 plus tangent square theta. Guys, I just had written those 3, and one of the one that we actually used in here as well is the same one. So to get the secant theta, so secant square theta, if secant square theta is that, if I want to get the secant theta by itself, obviously I have to take the square root, right? To get secant theta, you take the square root on both sides. 1 plus tangent square theta. This is my tangent theta. What would be my tangent square? Obviously, I got to square both sides, so it will be x squared over 4. That's it, guys. I have secant theta in terms of x as well. I have tangent theta in terms of x as well. Yeah, they don't look so nice. You may think that they look ugly, but this is what we got, right? So we just got to bring it all together and write our final answer. So the final answer is going to look like ln, and then instead of secant theta, I got to put this radical piece, the square root of 1 plus x squared over 4. And then plus tangent theta, which is just simply x over 2, and then there is a plus c. Guys, this is my final answer. This is the final answer in terms of x, and it is supposed to be in terms of x because the original function is in terms of x. Final answer. Guys, again, there was a lot of steps, and just looking at this, it seemed like how are we going to use a trig technique, but we have to recall the trig identities. And guys, there's so many of the trig identities, one has to be able to identify which one to use. Guys, if you have something of this type, it is convenient to use the tangent, but then I use 2 here because I saw that 4, and then from there I was able to simplify and finally get the final answer. So guys, again, some of this is clever substitution, some of this is tricky. So for example, instead of 4, if we have let us say we have a 16 here. So if I have a 16 and I know I want to get a 1 finally, then I should not be using x equals to 2. I should be using x equals to 4 tangent theta, because then I will be able to get 4 squared is 16, and then I can take out 16 as a common factor instead of 4, and I will get 1 plus tangent square theta. So guys, one has to not only understand this problem by itself, one also has to understand the techniques and methods used so that when one has to do another different type of an example, one can use those methods and techniques. So guys, spend some time thinking and looking and understanding this type of a problem, and then try to do more on your own from your textbooks. Till then, take care. I will see you next time with another method for integration.